Good morning. I think our numbers are good. We like to start outright because we have short time today. It's a 1-hour lecture. Thank you for those who have already registered their attendance, as well as those who are still joining. Remember, you can always use the chat section to raise your question as I continue with the lecture. All right. Let me just project this. Let me make this full screen for ease of but at least you can see it quite clearly the way I'm seeing it on this side. Okay, we are still the topic reduction to finite element methods. I mean that's our course unit, and we managed to look at 2 elements so far: the string element, the truss element. So today we are still looking at the truss element, which we call the bar element. But now we're saying one that we used last time was like this. So you can consider a scenario whereby we are considering a truss, typical truss. Okay. Let's say we are talking of a truss here. Okay. Truss like that. And we can just have a 3-member truss. We are saying that maybe it's just illustration. Okay. Or a support on the other end. So this is node 1. Let's call this node 2. Let's take this node 3. So this is element 1. This is element 2. And in fact, this is element 3. Okay, what else do we need? Now, we managed to, I didn't want to go this far. Sorry, I'm just using, my pad is misbehaving a little bit. But I wanted to highlight something here that last time we were looking at this element. Okay, we are looking at this one. One that, if this is now the axis, what we refer to as the structure orientation. The truss is oriented in that direction. So those axes we can define any point, any coordinate using the x and y as shown. So we considered this element 1, whose now this element, when you look at it, this element 1, when you look at it, it's oriented the same direction. You're talking of this element 1, it's oriented the same direction as now what we defined here. Look at this member. But how about element 2? You see it's inclined a certain angle here. Angle we can refer to as theta. And this is the element that we are showing now on your right hand side. And this is what we are calling bar truss element in 2D space. Each area, what we are just considering was 1D. That is, we were just considered with one axis. We could define any motion, any degree of freedom, any deformation, which was of course axial deformation, whether contraction or elongation. We could define using one coordinate. That is what in 1D space. Now, when it's oriented, because now we'll have the component in y and the x axis. Therefore, this is what we are referring to as a bar in 2D space. But just as a summary, because I've been mentioning about it, remember we talked about the local and global coordinate system. We said for an element, each element now will be oriented in its own coordinate system at elemental scale. Consider element 1. We consider this element 1. I can just highlight here. This element 1, I've got small y. We use small letter x and y. I've got a small y-axis, y and x. Okay. Now, when you look at element 2, in this one, I've got its own orientation, coordinate on this direction, small x, y, value, small y. You can see all the element, even element 3 will have its own coordinate system. Therefore, when we come now to the assembly stage, we need some, remember we are assembling different stiffness matrices of individual elements. We call the elemental stiffness matrix, get the global stiffness matrix. And therefore, we need to assemble, and you realize or you noted that assemble is just matrix operation is addition. To add, we have to add them when they are at a common coordinate system. And that brings us to the issue of we refer to as transformation. For elemental stiffness matrices, we have to transform them, not just stiffness matrices, but any quantity, elemental quantities in local coordinate system have to be transformed to a global coordinate system or to be aligned the structure coordinate system so that we can be able to add them up. Otherwise, you cannot add two things which are different. So, to do this, we need to obtain what is called a transformation matrix. Okay? And this is the core of today's lecture. How do we derive the transformation matrix? Transform from local coordinate system to global coordinate system. So you have noted that we have these notations. From local coordinate system, we use small xy, global capital XY. Local coordinate system, now the use and the use, remember you are just you had just been introduced to you because we were only concerned with the axial deformation along the x-axis. But now because we are going to have a component in the y coordinate system, remember the method of resolution of the joint, we're going to have a component. That's why we are now we are saying we are going to have a vertical component. We introduce V. U and V now. Local coordinate system, of course, we have one degree of freedom at a node. But a global coordinate system, because now we have U and V, horizontal and vertical displacement. Remember, we are talking now about displacement. Global coordinate system is the displacement at this node. If this structure deforms in whatever direction, instead of this member will have a component in the x direction, maybe y direction, depending with where the formation of occur or the direction that the deformation have taken. Okay. Understand what I mean here is that if our structure, okay, I think I have to give up this. I have a touchpad here which is helping a pen pad, but it's bringing more problems than helping me. Okay. So what I'm saying is, if this structure, let's say, deforms, okay? A structure deforms something like that due to application of load. So at this node, we want to get the deformation, have the x component, which we are calling u, and maybe the y component, if they are sinking, which we are calling v. And for element, we are using the small letter u and the small letter v. For the global, is a structure, we are using u, v, without the, you see this line, for this mark, so u plane, z plane, and here u, good. Enough with the notations. Remember, don't forget this again, because we keep on referring to them. That for an element, bar element, the stiffness matrix is equals to A is equals to A E over L, okay? 1 minus 1 minus 1, 1. Don't forget that. Okay. Now let's see the transformation. So we have this. I think I need this for ease of drawing. It's fast. Please. Okay. Okay. So if you look at this element, it's the same element that we have, but now I've positioned it here. So what is let's first plot the axis. Let's first plot the global coordinates system. So we have that. And we have, of course, now in this direction. Okay. And this one now we have, this is the Y, capital Y. This is the capital X. So we are going to transform all the components into this coordinate system. So let's consider this node. We have two nodes, node 1, which is called node I, and node J. Now at node I, just for the same element, you see it have got its own coordinate system, elemental coordinate system, or coordinate system, small x, this one, and small y, okay? Of course, the coordinate have to be a right triangle. Now, so we are kind of transforming, moving this to get the vertical component and the horizontal component. Now, you can draw, of course, you can complete this angle because we are going to use two things. We are going to use geometry and trigonometry, which is something I know you are familiar with. So what we do here, I can plot, because this line, you are seeing this line here. Okay. This line is parallel to this. I can draw a line parallel to this axis. Okay, here. So I end up having a right angle triangle here. So my triangle, this triangle is right angled. Okay. Let me extract it for you so that maybe you can see it a bit clearer. So you're saying I have this right angle triangle like this. Okay. This right angle here. Okay. And we are saying this angle is theta. This component, we have it u prime I. Okay. And then we have a component. Okay. We have a component UI in the global coordinate system. This is the axis capital X. This is the axis capital Y. But I just wanted to extract this triangle for you so that you can see it. So we are using this triangle. We're using this triangle to get the different components. So this is your element here. Don't forget. Okay, this is your element. This one here. We want to get the vertical component of the same and the horizontal component. So when you use this angle theta, before I leave this place, it's also good to know. Okay, let me just finish it at this part. Using this angle theta, you can see this right angle triangle. U prime I is the horizontal, use this. I know you know about this SOHCAHTOA. Okay. Whereby we say sine, cos, and tan. Okay. There's a hypotenuse. So the horizontal, or this UI, when you look at this right angle triangle, the way it is, then on the x-axis, when you want to get the component, this is the adjacent to this angle theta. So you can say cos theta equals, cos theta is equals to what? U adjacent of hypotenuse. So U prime I over UI. Therefore, we have the horizontal component of UI, U prime I, which is equals to UI cos theta. So in a similar manner, remember, we have a component, the capital VI here. not the capital, but VI without applying, which of course is here. Can drop that here. So we have VI here. Now, when you look at this triangle now again, hope I'm not losing somebody. When you look at this triangle, you have formed another right angle triangle here. And now the right angle is here. So that if you use now the second triangle, you want to get the vertical component, okay, of UI still, the horizontal displacement, U prime I. So you see this one now will be U prime I is the hypotenuse, okay, the hypotenuse, and you want to get opposite, so use sine. So we can say cos theta again is equals to cos opposite, sine, sorry, sine theta is equals to opposite, which is VI over hypotenuse. Sorry, something is amiss. Something is amiss somewhere. Something is amiss somewhere. You need not drop that line there. Let me just repeat this. Yeah. Okay. So sine theta is equals to VI. Sine theta is equals to UI, that is opposite over VI, which is hypotenuse. Are we missing something here? You following? Anybody following me here? Because I'm just trying to get the rectangles, right angle, triangles, sorry, that we can use similar triangles. We started with this triangle, the one now is on screen, and we are able to get the horizontal component, okay, UI. Yeah, we are able to resolve the U prime I into UI in the horizontal component using the cosine. Now we wanted to get the same, but now the vertical component. Okay, so it's vertical component. Of course, definitely it means to get this vertical component, let me introduce something else here. So if you go back to our triangle here, I bring back my triangle so that I have space for working. So the line that I was drawing here, I could extend it. This line, I plotted the line here. I could extend it to this part. Okay. Okay. So that when you look at this, we have this was the right angle triangle, and then this is a right angle triangle. Of course, using similarity, okay, if this angle is theta, this angle is 90, then this is angle is 90 minus theta, okay? Then if this angle is 90 minus theta, and of course we know this big angle here is 90, then this angle here is theta, right? So you have theta, we have this is the vertical VI component, okay? And we have the U prime I here. So you have the U prime I, this one. We have the VI, and of course, I wanted space because now I have extended this line here. I've extended that line there, okay? So we can be able to get the vertical component here or resolve this UI into this vertical axis by using sine. So you see, we have this. We know this UI and we want VI. So we know the we have the hypotenuse and we know the opposite of this angle theta. Opposite, UI is opposite. So that's why we are using sine. So we can say sine theta is equals to opposite, which is u prime I over hypotenuse. Remember, we are using this right angle triangle. We are using this angle on the top, on the upper part of this element. Okay, so this side VI is a hypotenuse. So VI. Therefore, VI or U prime I is equals to VI sine theta. Okay. Now, let's now add them up. I want to add them up. I want to add them up. So what we are saying is, we are saying that UI U prime I have got two components, which is equals to UI cos theta. So of course now this is this one that I've brought to this side. And now we can bring the other one here, okay? The vertical component. So you're saying again, U prime I is equals to VI sine theta. So you can add this to have overall UI prime is equals to UI cos theta plus VI sine theta. Just hoping we are together so far. Now, the second part, which I would like you to somehow visualize here, is to get now the component of the VI. Remember, in this axis here, we have this component VI prime. Remember, within the linear, we say the linear range, where we say that our element will only, deform by axially, that is stretch or compression. For at the element scale, the VI prime is just a fictitious value. I mean, our truss member is not stretching in that direction. But of course, for the structure, the truss, yeah, deformation of the node can be vertically and horizontally. So what you do here, we extend this axis, this direction. So remember, this now is negative capital X. And then we can draw the same way we drew this line parallel to this. We can plot another line, okay, parallel to this member here. So we plot another line parallel here. This is parallel to this axis. Like we are just taking this axis here. Remember, this one was parallel to the elemental y-axis on scale. This one is parallel to the elemental x-axis. Okay. So with that, when you do that, and of course we can extend here so that we'll have right angled here. So the axis, the x and y axis are the one that are making the right angle for the triangles that we want to use. So you're going to use this triangle and this triangle. Okay. Remember, on this direction, now this will become negative UI, because this is UI on this side, but now on the negative side. We have the VI here. Remember, you have VI prime here. So what else do you need? You have, of course, you can now use similarity. If this is theta, this is 90 minus theta. This is 90. This is 90 minus theta. So this is theta. Okay. This being theta, this being 90, this is 90 minus theta. This being 90, of course, this now being 90 minus theta, and then you take the big triangle here, 90, then this is theta. So I wanted to get this angle. and this angle. Use this triangle and this triangle now to get the vertical component. In similar manner, you are going to get vi prime is equals to vi cos theta on one x-axis, and vi prime is equals to minus ui sin theta on the horizontal scale. And when you match these two, you're going to get vi prime is equals to ui cos theta plus no, we need to correct that. You're going to get minus ui sin theta plus vi cos theta. So it's very simple thing to do to derive. Just have clarity as you are projecting this line so that they don't confuse you. So I've left this. I'll just move quickly in this one. Of course, in the interest of time, you don't have ample time, but again, it's something simple. You can be able to derive that so that I can get to the core of what you want us to do. You know, now you can write this together. Okay, u prime I is equals to ui. Let's start with the let's arrange in terms of, you know, ui vi, of course, it's like that. So ui cos theta plus vi sin theta. I'm just putting them together, and therefore, and the v prime I is equals to minus ui sin theta plus vi cos theta. So you can write in matrix form u prime I v prime I, okay, that's a displacement vector, is equals to, so you see this is cos, let me just write c, sine minus sine cos, yeah, and then we have u I v I. In short, we are saying u in local coordinate system, so let's say u prime is equals to this matrix, which can say t tilde, just a notation, u in the global coordinate system. If you can read the local coordinate system, the deformation local coordinate system is equals to a transformation matrix multiplied by the global coordinate system. So you can see you have been able to transform. You can be able to transform the local coordinate system, the deformation in local coordinate system, to global coordinate system using a transformation matrix. But this transformation matrix is not complete because we just transformed this node I. So the same will happen when we come to J. Okay, the same will happen when we come to J. Let me get this space here. So when we come to J, the same thing. Actually, nothing changes, only that now the notation is J instead of I. Okay, so that we are going to have the same equation. I'm just erasing this. Okay. But now for J, we are going to have uj, u prime j, v prime j, and that is the second node, equals to cos sine minus sine cos uj vj. Hope you are together up to that part. And now what remains, of course, now to describe the whole, to transform the whole element, you know, the two nodes together, we can get, we can merge the two equations. We can merge for the i's, the two nodes, and the j's, so that we'll have, of course, remember, At the top here, as I said, because this matrix, when you come to margin, you can kind of say this is a component J, U, Uj, Vj. Here, this is a component for Ui, Vi. Okay. So to merge them, just the same way we are doing, Ui, Vi, of course, prime, U prime J, V prime J is equals to, it's just a combination of this matrix. You can use superposition. So of course, here at the top, you'll have Ui, Vi, Uj, Vj. Now we have the displacement vector, Ui, Vi, Uj, Vj. Okay. And with that now, we can be able to look at common terms. We look for U prime, Ui prime, we have cos. On here is J, so they are not sharing the node. So you have cos. When you do this, you're going to have cos sine minus sine cos 0, 0, 0, 0. You're going to have 0, 0, 0, 0. I'm doing this faster because we already now are familiar with this superposition method. Okay. So now I've been able to merge the transformation of coordinates at the bone nodes from local to global. So you see, from local, the U primes and the V primes, to global, U and V, using a transformation matrix. So this here is what we are calling a transformation matrix T. Okay, at that point I can clear all this. Then we move to the next. Move to the next. All right. So this is what I'm talking about, equation 1. Okay. I didn't want to project this equation so that you don't now start asking where it's coming from. Now, you can mention two things here. You can always cos the cos theta. These are referred to as directional cosines, if you are aware of that. Okay. The cos theta, the sine thetas are directional cosines. And cos theta, you can use the notation L. Sine theta, you can use the notation M. They are directional cosine, of course, where like cos theta will be equals to xi. Okay. Cos theta will be xj minus xi. Okay. Xj minus xi over L, the length of the member. And of course, sine theta, which is equals to M, is equals to yj minus yi over L. So anyway, don't be worried so much about this. You can either use cos C. I've just summarized, I've just used a small C so that I simplify my writing. So as you can see in this equation, the first component here, we had labeled it as small, T tilde, to represent a part. So our equation here can further be written as, can further write this as, from local coordinate system. Remember, this is in bold, so this means it's a matrix. Local coordinate system, U prime, you need to pre-multiply the global coordinate system or global coordinate quantities by a transformation matrix T. Now, this overall T is composed of the small, the transformation matrix of the node T tilde, T tilde. You can see this component here is the same component here. So this is in compact form. At any quantity now, any quantity in local coordinate system can be transformed into global coordinate system using that transformation matrix T. Okay. So, like if you want to get the force in global coordinate system, you just need to, we have it in local coordinate system at elemental scale. You just need to pre-multiply the global quantity with the transformation matrix. And remember, I know you know this, the order of matrix operation is very important. Okay. This T being here is not the same as the T being after F. Now going forward, Going forward, you can be able to obtain for the same. Remember, at the local coordinate system, this is just a recap. We had the finite element equation. Elemental finite element equation is equals to EFL, that is K, okay, F. Yeah, this one we know that F is equals to K U. So if you wanted to say K, we could say local coordinate system. Now we can introduce these prime symbols so that we have F elemental. This is what now we have. We're just putting this. This one is what you have in your note previous class, but now we are introducing this prime to show it's in the local coordinate system. Because what remains is to get the stiffness matrix transformation or transform stiffness matrix for the whole structure. Okay. So this equation, when you see argument, it means you can you expand it to include, argumenting this equation. What we are just saying is that this equation, the one at the top here, just had the U and the V. UI, UJ. But now we have brought about, because of the nature of the orientation of our member, we have the vertex of V component. That's the one that we are introducing. So you're going to just argumenting, expand it, UI, okay, UJ, UI, VI, UJ, VJ, okay? Because of course you can see this element, UI, VI, UJ, VJ. As you can see, we say there is no force. For this member, there's no force acting on this node like this direction, okay? So at the elemental scale, these things don't make any sense, eh? But at global scale, of course, we're going to have this force component. And that's why you are finding this one being 0, FJ. This FY, we only have FI and FJ because the force is on this direction. We do not have force in the vertical direction. So this is 0, this is 0. And therefore, of course, you can see all these columns, arrows and columns are 0. The ones associated with VI and VJ. But we are doing this so that you can be able to do summation, as you are going to see slightly ahead. So this is what I was saying. You can write now, our equation can be written as K prime U prime of F is equals to KU. This is our finite element equation. So in our coordinate system, remember to include these prime symbols. So using transformation given in equation 2 and 3. Remember in equation 2 and 3, we said any quantity, that is F and U, can be transformed into global coordinate system by pre-multiplying the global quantity with the stiffness matrix. So remember we said F is equals to T times F. You see, this F here is equals to this part. This was equation 3. Now, U, we already derived it. We spent a lot of time deriving that. U is equals to pre-multiplication by transformation matrix, U. Okay? And then, of course, our K. This is the K we want to know. This is the K. Or we want to know how to move from local coordinate system to local coordinate system for the stiffness matrix. Now, looking at this equation, okay, looking at that equation, we can be able to pre-multiply. Look at our equation here. Yeah. F is equals to KU. In global coordinate system, of course, already we have the F and we have the U. If you remove this T, everything comes on this side, you'll have the equation for global coordinate system. And what we do, we can multiply. One thing that you have to note with this matrix, one of the characteristics which we are utilizing from this matrix is that the matrix T is, this matrix T, if you look at it, it's orthogonal. Okay? The matrix T is orthogonal. And orthogonal matrices meaning they are transpose. If a matrix is orthogonal, we are saying the transpose of that matrix is the same as its inverse. Matrix operation, for those who created time to look at it. So the transpose, when we say a matrix is orthogonal, we say its transpose is just the same as its inverse. So once you understand that a matrix is orthogonal, then you don't have to determine to get the inverse, you just need to transpose. And transposing is easier because we exchange the rows values with the column values. We interchange them. Now, utilizing that fact, we were utilizing that so that we could be able to move quickly here. So what we are saying is the same. Remember, to remove the t from this side, we needed to pre-multiply with the inverse. You know, if a matrix multiplied by inverse, you are left with identity matrix. Identity matrix, of course, in the matrix world, is like 1. So we want to be left with 1 here, just an F on this side. Okay. And therefore, we wanted to get the inverse of this matrix T. Now, using that advantage, utilizing that advantage that T is orthogonal, now we can just get the inverse by getting the transpose. Okay. So T transpose, okay, you multiply both sides by T transpose. On this side, we are left with identity matrix I, which is equal to 1. Okay. And on this side now, you can see it's T transpose. We have brought it on this side. Order is key. Order is key, right? Order is very important. Remember, this one, if order was not important, we could say, why don't you take this T transpose times this T to get identity matrix I? But see, we have K prime on this part. Okay, elemental stiffness matrix on this part. It's coming in between. So our operation will be first operate the first ones, the first two matrices, the resultant matrix that you get, then you do the operation, the T, then whatever you get, you go ahead like that. So order is key in matrix operations. Now, with this, remember the nature or the form of our equation of global finite element equation, or even elemental finite element equation. We say F is equals to KU. So F is equals to KU. We have this U. So everything else here is a capital K. Yeah. For your understanding, you're saying F is equals to KU. This is the U. This is the F here. So all this is K. And therefore, the elemental stiffness matrix in global coordinate system K is equals to T transpose K prime T. And that's now you've been able to transform or to obtain the global stiffness matrix from Moko stiffness matrix. So anytime we have a structure having different elements oriented in different coordinate system, you first determine the elemental in their elemental coordinate system or the local coordinate system. First, you determine the matrix in that orientation. But now when you come to the assembly stage, to get the overall stiffness matrix, you have to first do this operation. You first have to transform the element to get the same equivalent at the global or in the global coordinate system. What happens when you multiply this? Again, some food for thought and also some practice work. Remember, you have T is equals to, don't forget some of this very simple equation. T is equals to L M minus M L, okay, 0, 0, 0, 0, 0, 0, 0, 0, L M minus M L. So that is T, okay. What else do you have? K. K in the local coordinate system, we have it as A E over L, right? 1 minus 1. Now, for you to be able to operate this, that's why you include the zeros. So 1 minus 1, no, you have 0. Then you have 0, 0, 0, 0. Okay. Then you'll be minus 1, 0, 1, 0, and then the bottom one is 0, 0, 0, 0. They look like binary numbers. So you have this, you have this. Of course, from T, you can get the transpose because you just need to interchange these rows. They become columns. Every row become a column. The column members become rows. And then you do this multiplication, which again, that's matrix operations, which I don't intend to go into that direction. So what I'm just going to give you is the overall equation. Once you do this operation of multiplication, this is now what we are looking for, the transformed or the global stiffness matrix. Okay, K is equal to E of L, and then all this. And looking at this, of course, we are not called to memorize, but there are things which are very simple that you don't have to be given in an exam setup. Because you see, this thing is repeating itself. This with positives comes this part. Then what you just need, main diagonal, they are positive. It's the same thing. And then minor diagonal, they are negatives. And that's the equation that you use to obtain or to transform from local coordinate system to global coordinate system. Of course, now from that point, everything else now goes. The same procedures that we have been following. Once we assemble the stiffness matrix, we just proceed the same manner. You introduce the boundary conditions, you solve the equations, then to obtain the unknown quantities, deformation, maybe forces, and then you can also start recovering derived quantities like the stresses. And in a similar manner, in this slide, I just want to highlight what we already derived from the previous class, the elemental stiffness matrix using strain displacement matrix B. Okay, stress is equals to Young's modulus times strain. The Young's modulus, we are able to express it in terms of displacement vector and strain displacement matrix. And in this format, you expound it. It's very simple to obtain that, or in compressed format, this is it. Okay, what have happened here? We have just taken U's, because in terms of stress for elemental, remember we are talking of element, not the global element. There is no stress that will occur in the y coordinate. Okay, the y, small y. That's why you see we are just concerned with U, I, and U, J, the U components, the axial components. So don't ask yourself why have our matrix condensed. It's still our matrix that we are using, the transformation matrix. If I take you back to it, still our transformation matrix. Okay, our transformation matrix that we derived, but we are removing this component, the V's. So we are removing the second row and the second column. I mean the second row and the fourth row, the ones associated with V's. Okay, that's why you are seeing LM 00 and 00 LM. Good. Well, derivation may seem scary, but when you come to application, it's quite simple. And we can do so now by looking at a simple example. Let me first see whether there is any question. It seems that most of you are together with me. I don't know whether you'll be able to finish this question because we only have about 8 minutes, but we need to do this one to enable you to understand or to appreciate what you have just derived. Don't want it to evaporate. So you're given a simple truss, very simple plain truss made of 2 bars. I'm moving ahead because I can see no question raised so far. So good. And you're given the material properties E, the geometry A and L. There's a load applied at node 2, node P1 and P2, horizontal and vertically. You are required to determine displacement at node 2. And of course, stress in each of the bars. Okay, let's go straight ahead with this. What you need to have here, or to know, of course, this one should never get out of your mind, that this is for elemental stiffness matrix. This is EA of L. 1 minus 1 minus 1, 1. Okay, that's always like that. It doesn't change. Then remember the stiffness matrix. We needed to get the stiffness matrix, the global stiffness matrix. This is local, K plane. So you don't need to go through the derivation process. You just know that at the global coordinate system, okay, you know at the global coordinate system, K is equals to EA of L Okay, we know K, the global constant system is equals to EA over L squared, LM, M squared. So once you just know that, the rest is the main diagonal are the same, the minor diagonal negative. So I can start with the main diagonal to finish this row. Minus L squared minus LM minus LM minus M squared. Okay. Minus L squared minus LM minus LM minus M squared. And then, of course, main diagonal, the opposite is L squared LM M squared. Yeah, this is the equation that we need to use to obtain the global. So K1 global, K2 global. So what are these L's? Remember, L is equals to cos theta. M is equals to sine theta. Okay. Okay, you have the angle 45. The angle 45. So here is expressed in sines. Why? Because now you start punching calculator. You know it's good to be smart in your workings. These are some of the things that you studied maybe in geometry, okay, either in high school or in first year. If you start, if you just get this value, cos theta in your calculator, and then you get it decimal form, you have a lot of calculation, and you have numbers to keep working with, large decimal places and all that. So instead of that, now we opt to use special triangles. The isosceles and equilateral triangle. Cos theta is given as √2/2, and sin theta the same. Now, how do we get these angles? You see this? You remember this unit circle? Something called, we are saying cast. Okay, I don't know how you used to remember this, but all angles are positive here, sines are positive, tans are positive here in the third quadrant, and only cosines are positive in the fourth quadrant. Then, this being the horizontal x-axis, we measure our angles counterclockwise. Okay, so this is nothing new. It's just something that you know, something basic. Now, then number 2, we measure our angles from node I. We read node I to node J, where I is less than J. I is the smaller node. So if you're talking of element with node 1, 2, or with node 5, 6, you can't start reading your angle from node 6 coming to 5. Look at this. We have node 1, node 2, this element 1. So we read from this node, this is the orientation. So we know this is the orientation of our member, and this is the x-axis for that member, and this is the y-axis for this element or member. Now, from the horizontal x-axis, angle is 45. Similarly, when you come to element 2, okay, we are given this angle is 45, but element 2, the row node is 2 to 3. So we read the angle from this point, and then we are going to read it from the horizontal x-axis this way. So this is the angle that tells us the orientation, because we are reading from 2 to 3, from lower to higher. So this angle is, of course, this being 45, this is 45, this is 90, this is 145. So theta 2 is 145 degrees. So always note that. Otherwise, if you read the opposite, of course, you are going to get the same, maybe the same values, but sign, the sign may change if you don't read properly. You don't follow that procedure. Okay, so what do we do? Now, we know L for element 1, L and M is equals to √2/2. So you are just multiplying here, √2/2. Even then, this tells you if the quantities are the same, L and M, cos and sine, even LM is like a square of the same. So it seems all these are squares. Okay, if we square this, so like if we say L squared, this would be 2/4. Okay, or it would be a half. So this tells you that all these quantities, they are a half. Therefore, we can move the 2 outside so that we have only 1 inside. Okay, it's like we are going to have K is equals to E. What is E? We are told that E and A remains. L, and then you can move 2 outside. Then this one just becomes 1. Because I have here now the only one. We just factored out 2 here. So we're going to have 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, minus 1, minus 1, minus 1, minus 1, 1, 1, 1, 1, as the stiffness matrix for element 1. So you can see application is very easy indeed. Only that what you have to be careful with is the sign convention, how you read the angles. Let's do the same for element 2. Can do the same for element 2. Okay, we have done for element 1. So for element 2, theta is 135 degrees. We have agreed this. We have agreed that we are reading from at node 2 from the horizontal x-axis. So this is 135. Okay. So it doesn't matter if this element 1, the node 1 was here, this was node 1 and this node 2, we would have started at node 1. This is the horizontal x-axis, and then we read all the way like this, because we become from node 1 to 2. That's a sign convention. Okay. Then with cos 135, of course, you know this is a complementary angle of 45. You can use cast, or you can use your triangle. You can use the unit circle, or you can use your calculator. This tells you that in this circuit, because we know cos 135 is on this quadrant, the second, only signs are positive. So it means only M will be positive. Cos, which is L, will be negative. Again, remember from our matrix, cos and sine for 45, they are the same. So it means L squared and LM, all these are squares. Again, you square. So that not to express K2, you'll have, whether you square, whether you multiply L times M, of course, the same thing, because the quantities are the same, only the signs now change. Now, here is where you have to be very careful about the signs, because we have the signs. If I take you back, I can take you back. Okay, no need to take you back there, because we can still have it here. You can still have it here. Okay. You can still have it here. Let me just erase this part here. Okay, no problem. It's not working. K is equal to L squared LM minus X. So you have the negatives, you have the negative signs in the matrix itself, and now we have these negative signs here. Okay. So be very careful when you are doing the pre-multiplication. So when you do the pre-multiplication, of course, again, we can factor in. If you square this, you're going to get this as halves. You can factor out the 2. So in the same manner, we're going to get EA over 2L. Then the others, because of the signs, 1, M is B minus, okay, 1, minus 1, 1, minus 1, 1, 1, minus 1. This one becomes minus 1, 1, 1, minus 1, 1, minus 1, minus 1, 1. Okay. So far, so good. Okay. Going forward. Going forward. So this is it. Okay, to remember the U's and the V's, I said you put them here to assist you. Now, we have K1 and K2 in global coordinate system. What it means is just to assemble the same way we did with other matrices. So if you have done enough practice, now you should see this as something very easy to do to obtain this matrix. Because you just need to add K1 and K2 to get this equation, this matrix here, to get the overall, to get this. Okay. So you see, why we are able to add, before we could not be able to add the different matrix because the two elements are oriented in different coordinate system. But now, once we have been able to transform them into global coordinate system, now we can go ahead and do the summation of the two matrices. From here now, things becomes very easy. Now you can start appreciating why I was saying that this method requires us to employ computers, because just two elements oriented in different coordinate system. Yeah, if you look at this, and we have not even considered the 3D, which is the reality actually. New life things are in 3D. So we could be talking of a space truss. But here we're just talking of a plain truss. X and Y. Again, they have just two members with 3 nodes. In each of the nodes, there are 6 degrees of freedom. That's why you see now we have a 6 by 6 matrix. Now you can imagine for a typical trusses that you have been solving by other methods like precision of joints, how many nodes we have, degrees of freedom, what will be the size of our matrix. And now operating on these matrices becomes rather tedious. That's why we need now to utilize the softwares. But now with this understanding, as I said, use simple examples to understand the concept. Whatever now will be happening when you are utilizing the softwares, the abacus, and I hope a number of you have downloaded that, or all of you have downloaded and installed in your computers, because you'll be using it, you'll be utilizing it very soon. You could be you could be doing practice on the same with the solved examples that are given there. And for our assignment 1, remember the first part you could have done the first day. The second part now you can do after today, because we have been able to see how to solve for a truss element using the finite element method. Now the third part now will involve, with the same assignment, will involve now you using the software to solve the same joist problem. A joist is just a truss. Okay. Now, once you reach this stage, you have the global finite element equation. Nothing much now remains here. Just follow the procedures that you are following. Bring in the boundary conditions, reduce your equations, solve for the unknowns, nodal unknowns, and any other derived quantity that is required. So what do we know so far about the boundary condition? We want to define the boundary value problem. This node is fixed. Node 3, node 1 is fixed. So you look at these quantities. At node 1, you have UI, VI. You have UI in that direction, VI. These are zeros. So UI, U1, V1, U3, V3 is equal to 0. What else is known? Forces are given. P2, P1. P1 is F1 in the direction X. F1 in the direction X. No, sorry, there is F2. This is node 2. F2 in direction X. P2 is equal to F2 in direction Y. So substitute those known values in this equation. Okay, this is what I'm saying. The boundary conditions, these are known. And some forces, applied forces are known. So you go ahead. If we put 0, this becomes 0 here. You know this is 0, this is 0, 0, 0. What does this tell you? You can remove the rows and the columns associated with 0 degrees of freedom. So you can remove this first row, second row, 5th row, 6th row. In a similar manner, you can remove the first column, second column, 5th column, 6th column. What are you left with here? Some very simple thing. This one, this one. And you see our equation now, by just employing the boundary conditions, our equation simplifies, okay, to this. E over 2L, 2002, and all that. So you can solve this now. Yeah, this is just a simultaneous equation in two unknowns, U2 and V2. Using the first equation, you can solve for U2. The second equation, you can solve for V2. In fact, these are not simultaneous equations, they are just linear. They are not simultaneous because the first equation I've got only one unknown. How? Okay, we can say they are simultaneous, but the second quantity for the first equation is 0. 0 times V2 is 0. Okay. So in a similar manner, the first quantity, yeah, the U2 in the second quantity is 0. Okay, so very simple. You solve that, you're able to obtain what is U's and V's. Now you can use the equation that you derived in equation 7 for stresses using strain distribution matrix. It was given as follows. Okay, sigma 1 is equals to E over R. So what is that equation that you're employing? Did you forget this equation? No, this one. This is the equation number 7, which you have in your notes, I believe. Okay. So you just need to substitute this directional cosines, the M's, the M's, the LM. Taking note of the signs. You just substitute that. You have derived U. When you come, let's say, we have two elements, U1, element 1, element 2. So this I for element 1 will be U1, V1, and U2, U2. This is what now we are doing in this. This is what we are doing in this slide. So just substituting these directional cosines. -1, -1, 1, 1, LM to get stress in bar 1 is equals to √2 over 2A, P1 plus P2. And in bar 2 is equals to the values given. All right. I think that's enough for now, because what remains now is to attempt this question. This example, the second one, is similar to what we have just covered using the same principles, only that now we have something we say multi-point constraints. It's constraint in different points. And again, remember you said the finite element method, one of the advantages is that it can be able to solve complicated boundary condition. Okay? So you can see node 3, in this particular case, the orientation. Yeah, you can see how the boundary condition is oriented. If this was to move, because this is Aurora support, if this was to move, you see it's moving in this direction. Okay. If this was to move, this moves in this direction. So you can see these are a little bit complicated boundaries. Eh? But first things first, you don't have to worry about that because that's about the boundary. At this point, we say boundary condition of any quantity, whether it's force. Remember, boundary brings about, they define the displacement and they also bring about the reactions. Now, the first thing that you need to do is to get the global finite element equation. And to do so, you need to get the global stiffness matrix for this structure. So this is a question. Now, the value of the load applied at node P is given. The length L here is given as 1. Remember, with this angle 45 and this being right angled, of course, you can get the length of all the other members. The Young's modulus is given at 210 GPa. This is steel. This is the typical Young's modulus for mild steel. Okay. Then the area for element 1 and 2 is the same. So this element 1 and 2. Remember, another thing you have to notice that for this example, we already have discretized our structure. So that's why you see the nodes are defined for you, the elements are indicated. But I mean, if you have to solve this and you're told to solve using the matrix method of structure, which is the same as things say finite element method, you don't have to have these elements shown or indicated. It's you to decide using the criteria that you said, how you locate nodes. It's you to define the node locations, and of course now decide which the naming of your nodes and the element. Okay. Now the A for element 3 is also given. It's different from the others. So you are required to determine the displacement of reactions. So displacement, So even looking at the support, if you look at support 1, it's pinned. And this being a pin joint, of course, we do not allow rotation to occur. Okay. Because no moments are going to develop. So U's and V's and node 1 is equal to 0. Now, looking at the support 2, being a roller support, you can have a vertical component and a horizontal component. So V at node 2 is equal to 0. Okay. These are things that you do by observation. V at node 2 is equal to 0. But U, because of the roller support, is a quantity you need to determine. Now, the interesting one is node 3. Node 3, we can only say with confidence that V prime 3, V at rock coordinate system is equal to 0. Because the V at the global coordinate system is the one vertically up. And the V at the global coordinate system, V3, is that direction. So if this roller support, as a result of this applied load, we expect to have a movement upwards. As the support moves upwards, we are going to have a component displacement, V3 global is not equal to 0. Only this support will not lift from this, it's a roller. So this support will not lift from this base. So that's why we are saying V3 prime is equal to 0. And this is a fact that you're going to utilize later on. You see how we can be able to transform from local coordinate system to global coordinate system of what we know. This is a known condition. Now, simply put, first we determine the stiffness matrix, but at this stage now, it's something rather easy for you. First, you need to determine the orientation of each of the elements. So element 1, from the vertical coordinate system, this one is 90. Okay. Element 2, this one, so 2, 3, it's horizontal. The angle theta is equal to 0. And element 3, so we move from the lower node 1 to the higher node 3. So theta is equal to 45. So with that, you just need to take our equation, the equation for the stiffness matrix, global stiffness matrix, and we plug in the direction cosines, and we come up with those stiffness matrix for each of the elements, which is something that I found quite easy for you to attempt. Okay. Maybe what I can do here before I just get to this stage is to put it for you, just for the sake of your understanding. I can jot it down. So that we are saying for element 1, theta is equal to 90. Maybe you could put this down if you want. So 90, we know cos 90 is equal to 0, sin 90 is equal to 1. So L is equal to M is 1. Remember our equation, K, stiffness matrix, is equal to EA over L. This is something by now it should be at your fingertips. L squared, LM, M squared. You just need to know that. The rest is minor diagonal negative. Okay. Minor diagonal negative minus LM, M squared. And then main diagonal, positive L squared, LM, M squared. So once you have this, all that now remains is to substitute. So for element 1, we have that. So all these L's, where there is L, because we know there is 0, that one collapses to 0. Anything multiplied by 0 is 0. So this one becomes 0, 0, 0, 0. Okay. So here you can comfortably say K1 is equals to EA over L. So you can say E1, A1 over L1. Okay. This becomes 0, 0. And maybe at this stage, we can even factor in these values of E's and A's. I don't think it's much of a hassle now because we already given what are these. Okay. Or anyway, so the top row all contains L's. So it will be 0, 0, 1 squared is 1, 0 minus 1, 0, 0, 0, 0, 0 minus 1, 0, 1. Okay. So of course you can factor in what are E's, what are A's for 1. Same case, we come to element 2. Theta is equal to 0 degrees. L is equal to 1. M is equal to 0. Remember, cos 0 is equal to 1. Again, you do the same that we have done to the element, you're going to get K2. So for K2, let's substitute the values. We have E2, we know 210 and 10 to the power 9. We are putting them to the same unit. Instead of gigapascals, we just talk of Newton per millimeter, Newton millimeters. Then A, we are given what is A. But as I always say, be very careful when you substitute these values so that they don't increase your working. So where we have, remember this M is equal to 0. Sine 0 is 0. So where you have M anywhere, it becomes 0. Okay. These are just operations, matrix operations. Okay. Minus 1, 0, 1, 0, 0, 0, 0, 0. So similarly for element 3, this one you needed to determine the L. Of course, you can use theta is equal to 45. So L is equal to 1 over root 2. M is equal to 1 over root 2, right? And you can use this angle 45 to get the length. Okay. So K3, when you do that, it will be equals to your E A over L. So this will be 6 root 2 times 10 to the power minus 4 over root 2. This comes to how much? Oh, this one is a bit tedious. 0.5, 0.5, 0.5, 0.5. Remember, this one I'm giving you in the simplified form. To get there, maybe you may need to do some few steps. It's minus. Here is minus 0.5. Here is minus 0.5. Minus 0.5, minus 0.5. It seems like I could have factored out even half. Yeah, to half 1, 1 minus 1, or like that. Okay. For some reasons, that one was done. So it means you can go further and simplify these. Okay. Right. So you have it. You have the 3 equations. Yeah. What you need to be careful and note is that when you come to summation, know that this is which node? U1, V1, U3, V3. Because there are nodes I and J. For element 2, this is U2, V2, U3, V3. For element 1, this is U1, V1, U2, V2. Because why are you writing this here? When it comes to superposition, you have to be very careful. You don't add elements which are not at the interconnected node. Because we are going to add U1, U1 with U1, U1 in either of these elements. Okay, you don't want to make that mistake. So what that remains now is just to assemble the matrix, the stiffness matrix. Quite some work there, which again, I can leave it to you at this stage. Sorry, something is happening in my computer. Sorry. Sorry for that. Something not right. Yeah. Don't be worried about that. We are coming to that later on. So we already solved this one. No. You solved which one? We are here. Something very interesting. When I write using my attachment, since the other things cannot be erased, I say clear drawings. No, it can't. Okay. Sometimes these technologies, they misbehave. Okay, no problem. Even if it's all right. So I wanted to project now our equation. Hope you can, hey, you can see it. Eh? So our equation this now as a result of this is as a result of utilizing, superimposing the matrix. I wish this one could make this clear. If you can't, then I can first exit because I don't want to lose any one of you. Allow me to exit the same way I do exit. Because this to exit, you have to go to the end of the slides. Okay. Then I come back. Yeah. So after you have derived our equations, our stiffness matrices, once you superimpose, this is what you're going to get. So that's quite some tedious task that you need to use your calculator to punch those figures in. Now, one of the things that you have to notice that our stiffness matrix, as we always said, they are symmetrical. So the quantities in, if you take the main diagonal, the quantities above the main diagonal are the same. So in this case, we have utilized that characteristics, and then we have just written the quantities on one diagonal and then read symmetry. But for a student, I don't want you to be this lazy. I believe you can be able to write it in full. But with practice, after having enough practice, because what if this one shows you are confident because you just determine on the top part. What if there's an error in the top part? And then when you're punching the numbers in the bottom part, you realize there was an error. You're going to check yourself again. But if you are so overconfident, you're just going to utilize this symmetric condition. You might not be able to check. So let's be writing in full until we have done enough practice. Good. So apply boundary conditions. These ones are outright. The ones I was explaining at the beginning of this question, that the U at node 1, U and V, and node 1, U and V, and node 2, V2, and at node 3, V prime, 3 is equals to 0. Again, we know F2x in this direction, x is equals to P. And of course, we know as a result of rotor support, there's no reaction that can develop in this direction, the axial direction. So that's why F3 prime is equals to 0. Okay, so you see in our equation here, you do not have the local coordinates because this is a global finite element equation. So how do we utilize this, condition that we have here to help us reduce our equation and enable us to solve? Remember, the purpose is why we are given this is to fully define the boundary value problem and to enable us to solve the equation. The boundary conditions help us to even constrain. Remember, initially for the spring element, when we started with the first derivation, there was a case we said that there is a singularity And until we define the boundary conditions, we might not be able to solve. Okay, because in reality, what we are saying is that our structure is floating in space, what we call rigid body motion. Right. Now, with that in mind, something you have to note here, we go back to elemental scale because we want to transform from element to global. This is the equation we started at the elemental scale. Okay, how we said to transform one node, this is the first derivation from local to global. This is what we derived as the equation. And this matrix is one that we are seeing is tilde. This one that we scored T, the signs here. So we are going to trace this equation because we have a nodal quantity, nodal elemental quantity. We have nodal elemental quantities, not global. Okay, these are the ones that we want to transform from local to global. So utilizing the V3, we go to node 3. So you're saying U3 V3 prime is equal to this, then U3 V3. So the equation that uses V3 is this one. So this is V3, this is 3, where you have I put 3. And therefore, we can use the second equation, which reads, this one reads, V prime 3 is equals to minus M L U3 V3. Okay. And this is it. Minus ML U3 V3. Or in simple terms, like that, which we can simplify further to have U3 minus V3 is equals to 0, or U3 is equals to V3. You see, we have gotten a condition, some known condition. U3 is equals to V3. Okay. In a similar manner, again, you can go ahead and do the same for F3. Okay, using the same equation, because we said any quantity in our coordinate system can be transformed using the transforming matrix to global coordinate system. Okay, so for F3 again is the same. Okay, so the same equation that we are using for U, we could say F prime I, F prime F in the direction. So this one, if you say F prime I in X direction, so F prime Xi, F prime Yi is equals to this, then F U represent X direction, V is Y direction. Okay, so in short, if I was to write this would be F prime in the X direction, node 3. This will be F prime in Y direction, node 3. This will be F, now in global coordinate system, in node 3. In X direction, node 3. Sorry, let me not interchange the name. So you're saying it's F in node 3 in X direction, F in node 3 in Y direction. What are you given? It's X in node 3 in X direction. We are given the top row. So use the top row to get the equation that relates the local quantity to global quantity. So you're going to have F3X prime, F prime 3X equals to LM U3 V3. And this is what is here. Yeah, this is what we are doing here. F3X prime LM F3, okay, 3 is equals to this. Again, we have been able to obtain a condition. F3X plus F3Y is equals to 0. So we can apply the boundary condition in the structure. How? If you apply the boundary condition, U1, V1, and V2. Okay? U1, V1, and V2. So we can remove those rows, the first, second, and the fourth row. The first, second, and the fourth columns. We can remove them. Okay? So we can remove them. And then we also employ the conditions. You see, we didn't know this F3, but we can be able to utilize this equation and know F3x is equal to minus F3y. Then U3, we have also seen that from this condition, we have been able to derive that U3 is equal to V3. So these conditions help you to further simplify your equation, okay? By just substituting the values, U3, and then V3 is the U3. P, F3x, F3y is equal to minus F3x. So you see how it simplifies your work, eh? And your equation, you can be able to solve. Now you no longer have three unknowns. You just have two unknowns. And this is what it condensed here. And doing so, you can be able to solve for F3s and the forces and the reactions. I've shown that. So everything can be solved in very simple terms using those conditions. So you can see how you can utilize the information given. The question should be, the information that I'm given, can I be able to solve? You realize that if, for example, you did not utilize that, you end up having, you did not utilize this given, local coordinates, in local coordinate system, the given no node of quantities in local coordinate system. If you don't utilize them, then you would end up having equation in three unknowns, which might be difficult to solve. So they have helped us simplify our equation. So I like to stop there for today. And also I know that I've given you more than enough to digest for today. So leave it at that point so that you can do practice. You can practice on the same. And there are a number of questions, of course, you can get from the two textbooks that I give to you. Make sure the class rep, I hope you have shared that. Make sure you try those textbooks to get more work examples. I mean, there are so many textbooks and a lot of literature on the same, these finite element methods, this introduction, okay? So you try that to do practice on this. So any question before we can leave it? My other meeting already have started. So I don't know whether there is any concern, not even any other. Today we didn't have any question. I don't know whether the content was too conc or it was too easy. Usually I get questions, one or two questions, yeah, and then the other one via the room live question. Today we are not. I'm not going to share that live question and live link. Remember, any question that comes up as in the course of your practice, you can always ask us in the subsequent question that you can try to attempt. Okay. Okay. Thank you. That being the case, if there's no question, we stop it at that. So we meet again next week, and of course, thank you for joining on time. Utilize the resources that you have in this platform, the number of resources that you can utilize in your practice. So many solved examples. So you're not here by chance. You're here with a reason. All right, that's all for today. Next week, we move to the beam element, but not before you have done enough practice on this. And also, you may have to agree when next we need to have our first CAT. That's all. I stop this record.